we are looking at nodal analysis. Last time we did this problem 3.1.9. We can change that into this. Basically, when they said V out for 2 kilo ohm, they used a line, but sometimes it's confusing. So in the exam or quiz, you should be able to see something like this. I drew all of this, okay, with the PowerPoint. So in here. Now the first thing we need to do is what? Identify all the nodes. So how many nodes in this case? 3 plus 1 reference node. So we have these 3 non-reference node, and very bottom we have a reference node, and we're gonna call it as a 0 volts. What's next? Before we do KCL, exactly, we need to assign the directions of the current. So typically going from left to the right, and then top to bottom. That's what we want to do. And then now we need to do KCL for each node. That's what we did. And then there are 2 cases, just like what we have here as a 12 volts that is in between non-reference node to the reference node. If that is the case, simply we call this as the voltage, as a node name, and use this number to do the KCL. However, if you have the voltage source in between 2 non-reference nodes, then it's a problem. When we have voltage source between 2 non-reference nodes, there's no way we can find the current in terms of V over R, right? Using Ohm's law, because there's no resistance available in this node. Therefore, we cannot do that. So what we need to do, we need to make this as a super node. And then all the currents going out from the node. At the end, we need to have one more equation doing what? KVL, including this super node. So let's do this. We are asked to find the V1. Can we combine these two? That's the first thing we want to do. So let's combine these to 4K. 4K, they are same value and parallel. So it's going to be 2K. So we can use nodal analysis, or we can use simply current division. So let's use the current division first. We'll do nodal analysis. So for this guy is 12M. 12M is getting into this node, and it's going to split into these two. So find the V1, we need to find I sub 1. Once we calculate the I sub 1, okay, V goes to IR. I sub 1 times 5K, that is V1. Simply that's it. So if we do I sub 1 equals opposite, so this 5K is parallel to 5K plus 2K, which is 7K. So 7K opposite at the top, sum of all of those at the denominator times the total current going in, 12 milliamp. So that is 7 over 10, 12 times 12 milli. So that is 7 milliamp. Then what? Once we have I sub 1, V1 equals 7 milli times 5K. That is 35 volts. If I say just find the V1, then feel free to use any method you want. But for the quiz next week, it's going to be one problem nodal analysis, one problem for mesh analysis. That's something we're going to discuss today. So you have to use those 2 techniques. Now, let's use the nodal analysis this time. We need to identify the nodes, right? So this is going to be our V1. That's the positive at the top, so we can call it V1. And then assign the direction of the currents. We have this direction going in. That's a 12 milliamp. We cannot change that, so you need to be careful. There's a direction of the current is already assigned in the problem, so it should be that. And there is another one going downward. Now, let's do this. KCL at V1 entering 12 milli equals leaving V1 over 5K plus V1 over 5K plus 2K. So those are the series.
Hey, Dr. Kim, it's a nodal analysis. So do we have another node here?
That's true. And you want to do this as a V2, we can do that. If that is the case, we need to do KCL at V1, so 12 milli entering equals to leaving V1 over 5K plus V1 minus V2 over 5K. And also KCL at V2 entering V1 minus V2 over 5K equals leaving V2 over 2K. If you have two unknown nodes, definitely you're going to have two equations and two unknowns. If it's not, since these are the series, you want to combine these two as a 5K plus 2K, we can do that. And that way we have only one equation and one unknown. This from here, denominator, we have a 7K and 5K. So we're going to multiply everything times 35K. 12 times 35 equals 7V1 plus 5V1, which is 12. 12 times 35. So V1 equals 35 volts. And if you set it something like this as a V1 and V2, now we have from here multiply by 5, 60 equals V1 plus V1 minus V2. 10K, 2V1 minus 2V2 equals 5V2. First equation we have 60 equals 2V1 minus V2. For the second one, we have a 2V1 minus 7V2 equals to 0. Calculator, so V1 should be 35. V2 please. 10. Thank you. Yeah, so this is method 1. This is method 2. This is method 3. So your question is method 2? So the method 2, I use this circuit. Therefore, this whole node is going to be V1 plus this is V1 minus. Voltage across 5 kilo ohm resistor, it should be the same as voltage across 7 kilo ohms, right? So these two are parallel. They share the top nodes and bottom nodes. So in this case, we just need to have V1 only. But for this guy, is for this. Okay? So we V1 and V2. Do you see any other method that we can solve this problem? So we have here, what if we combine these two? Then we're going to have 35 over 12K. This is 10K. This is 12 milliamp. And then what's the voltage across this guy? 12 milliamp times 30 over 12K, which is 35 volts. Voltage across here is the same as voltage across here. So simply combining it and then apply V equals to IR, done. We can do that as well. Let's do this. One more super node. Step number 1, identify the nodes. So we have node here, 1, node here, 2, node here, and 3. We're going to name this node as a what? V1? No, this is the voltage source. It's in the diamond shape, kite, rhombus, whatever you want to call it. It's a voltage, but this is the dependent voltage source, plus and minus. If there is an arrow, that's the dependent current source. So depend on the value of V naught right there. So it's a voltage source, so I'm going to call it 1 over 2 V naught here. And in the middle, we're going to call V1. And this one, we're going to call V naught, because that's the V naught that we want to find. That's the step number 1. And then step number 2, assign the direction of the current. Well, actually, by looking at the nodes, 12 volts, we have a reference node at the bottom. But this 12 volts independent voltage source is in between two non-reference nodes. Therefore, we need to do what? Super node. Cover up this, and we're going to call it super node, and assign the direction. And we can go entering, leaving, and last time we said in the super node, it is easier to just all the currents are leaving from the super node. But again, it really doesn't matter, but we'll do that. So KCL at super node, then everything is leaving. V1 minus 1 over 2 V naught over 1K plus V1 over 2K plus V naught over 1K equals 0. For this equation, we're going to multiply everywhere by 2K. Then we have 2V1 minus V out plus V1 plus 2V naught equals to 0. And from here, we have 3V1 plus V naught equals to 0. Now we have a V1 and V naught. We need to have another equation where KVL including supernode. This guy is a positive V1 minus. This is positive minus negative. So we do KVL with the supernode. So entering negative V1 minus 12 plus V naught equals to 0. And from here, we have V1 minus V naught equals to negative 12. So now we have two equations and two unknowns. V out equals 9 volts, V1 equals to negative 3. The reason I wrote this one first is, as we discussed last time, when you look at this node, V1 minus V out, voltage difference from here to here, current going in that direction, right? Voltage difference between here to here, higher potential, lower potential. So we need to read that sign as a 12 volts. That's exactly the same as when you do the KVL. Yeah, so let's say if we use this guy, then should be 1 over 2 V naught minus V1 over 1K. That's the entering, equals V1 over 2K leaving, and then plus V naught over 1K leaving. And when you move this guy to the right hand side, we have exactly the same equations. So really it doesn't matter which way you put the directions of the current, but once you assign the directions of current, you are not allowed to change that in the one same problem. Yeah. It doesn't matter independent or dependent. So if we have something like plus minus 10 and then minus plus 10 V out. If you have something like that, this guy, we need to have a supernode because these two nodes, they are non-reference node. It's not 0. Voltage here is not 0. Voltage here is not 0. Voltage at the bottom is 0. That's the reference node. So this guy is the voltage right here. It's the 10 volts. And this one is 0. So the bottom one is always 0. And the top one, or possibly in the middle, it's not 0. So it doesn't matter independent voltage source, dependent voltage source. We're going to make this as a supernode. Yeah, this one, that's right. So if you do supernode here, so now we're going to go out, 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 and we're going to say this is 10, this is V1, this is V2. So in this first supernode equation, V1 minus 10 over whatever the resistance, V1 over this resistance, V2 over this, V2 over that equals to 0. KVL, for second example, KVL. So for this, you're talking about this guy, right? You need to do this. So the KVL for that is going to be negative V1 minus 10 V naught plus V naught equals to 0. Or simply you say V1 minus V out equals to negative 10 V naught, because we're reading from that. If you're reading from right to the left, V out minus V1 equals to positive 10 V naught. Yeah, good question. Can we combine these two? Yeah, of course. These are two parallel ones. Combine it, it's perfectly fine. And after we combine it, the voltage across here, the result of combination still be the same as V naught. Yeah, the supernode, it's going to be between two non-reference nodes. So this is two non-reference nodes. Why is that? So we're doing the nodal analysis. So we assign the direction of the current. Now, this current is going to be V1 over 2K because V equals to IR, I equals to V over R, right? So we are using this relationship, V over R. This guy, for the current, go through this 12 volts. There's no resistance, right? There's no R value. So that's the problem. So that's why whenever you cannot find the R, you need to use the supernode, including that voltage source. That's always the case where the voltage source is in between two non-reference nodes. So that's the nodal analysis. So now take a look at the mesh analysis or loop analysis. In the mesh analysis provides another general procedure analyzing the circuit using mesh current. Steps we need to go through: assign the mesh current and then apply the KVL, and we find the equation, number of equations. In this case, again, total number of mesh equals to total number of equations. Therefore, if you have two meshes, you're going to have two equations and two unknowns. If you have three meshes, you're going to have three equations and three unknowns. So let's do this. Mesh analysis. In the node analysis, we need to assign the nodes first, right? For mesh analysis, we need to assign mesh current first. So this is one mesh, this is one mesh. I'm going to call this I sub 1. I'm going to call this I sub 2. I do clockwise. I like clockwise. And you may say, hey, Dr. Kim, I want to do counterclockwise. We can do that, but you need to be careful. The following, the sign. That's the step number 2. For your quiz and exam, I'll give you the mesh current. So you have to follow this. Step number 3, we need to KVL at mesh of I1. So now we do KVL. So starting from 24 volts, this mesh current entering the negative terminal. So it's going to be negative 24 plus 4K. V equals to IR. 4K times I1. We have two more, right? So what do we want to write? Plus 2K I sub 1 plus 6 volts equals to 0. This equation is wrong. Why? Because I sub 1 is the mesh current. I'm pretty sure there's only current go through this 4K. That's the I sub 1. We okay with that? However, this 2K, the current go through 2K is not I1. It is actually I sub 0. Good point. But we want to write the equation in terms of I sub 1 and I sub 2 so that we can have two equations and two unknowns. Because we have two mesh currents, so we need to create two equations in terms of I sub 1 and I sub 2. Therefore, for the 2K, our reference current is I sub 1. So I sub 1 is our reference current. However, there is an opposite direction of the current I sub 2, upward. So that's, we need to subtract I sub 2. Now, let's do KCL at node A. What is this current? This outer loop, this side, 4K and this voltage, I sub 1 is only. For this side, I sub 2 is only 1. Therefore, what is this guy? I sub 1. What is this guy? I sub 2. So when we do the KCL at A, then what happened? Entering I sub 0 plus I sub 2 equals to leaving I sub 1. If I move this I sub 2 the other side, I sub 0 equals to I sub 1 minus I sub 2. We said 2 kilo ohm resistor. The right current is I sub 0, which is I sub 1 minus I sub 2. Exactly the same result. Yeah. I2 is entering this node. It's not going down or up. We do KCL, entering in the node equals to leaving from the node. So there is a I sub 2 and I sub 0 is entering to the node. I sub 1 is the leaving from the node. Yeah, exactly. So if we do at the top, and let's say this is B, KCL at B, entering, I sub 1 is entering, and I sub 2 is leaving, I sub 0 is leaving. So entering I sub 1 equals to leaving I sub 0 plus I sub 2. And we need to move this I sub 2 the other side. So I sub 1 minus I sub 2 equals to I sub 0. Exactly the same. So we got that first equation. And then we're going to write this in terms of I sub 1 and I sub 2. So I sub 1, we have I sub 1, I sub 1. Therefore, 6K I sub 1 minus 2K I sub 2 plus 24 if you, well, let's combine this first. Negative 18, move it over, positive 18. So that's our first equation. And the second equation, we need to do KVL at mesh I sub 2. So we're going to start from 4K. 4k times I sub 2 plus 2k times I sub 2 minus 6 going into the negative terminal of the voltage, and then plus 2k this time. Our reference current is I sub 2. Therefore, I sub 2 minus I sub 1 equals to 0. So now, if you put in this, negative 2k I sub 1, 2k, 4, 5, 6, 7, 8k I sub 2 equals to 6. The problem asks us to find I sub 0, and we did the KCL. I sub 0 equals I sub 1 minus I sub 2. That is 3.5 minus 1.6, and that is 1.9. Yeah. First of all, the mesh current, I sub 1, is the current go through 4K for sure, because nothing else. It's a pipe again, so water go through here. That's I sub 1. 4K, obviously there's only one current go through I sub 2. 2K, only one current goes through I sub 2. However, for this inside, one current goes in the downward and one current is going upward. When you calculate the voltage across to 2K, we cannot just say 2K times I sub 1. Wrong. 2K times I sub 2. Wrong. Because the current go through in the middle portion is one is downward, one is upward. So it depends on which one as our reference, as a positive direction. The second one should be the negative. Therefore, when we do KVL using I1, this I1 is our reference direction. Therefore, we have I1 minus I2. Minus I2. I2 is opposite direction. That's why it's minus 2. Right. When we do mesh I1, I1 is positive. Second one is a negative. When we do mesh analysis using I2, I2 should be positive, and the other one is the opposite direction, therefore it's a negative.